Alright. Hello everyone, welcome to 1.2 properties of graphs of functions. So today we're going to be comparing and contrasting the properties of various types of functions. So we probably did this last year. We introduced ourselves to all of these cool functions. F of x equals to x, linear, f of x equal to x squared, quadratic, h of x equal to 1 over x, rational, k of x equals to the absolute value of x, and that's just absolute value. M of x equals to square root of x, which is radical. P of x equals to 2 to the power of x, which is exponential. And Q of x equals to sine of x, which is sinusoidal. So first off, we're going to be stating the domain and range of each function, determining its zeros and y-intercepts, and determining the intervals of increase, the intervals of decrease, and state whether each function is an odd function or an even function or neither. And we're going to talk about asymptotes and if they're continuous or if they have discontinuities. And then we also got to describe the end behavior of each function. So without much ado, let's go ahead and get started. So let me drag this text back. Okay, so for f of x equals to x, we'll have the domain is x is all real numbers. Range is also y is all real numbers. So we have no restrictions. So we start off with the most easy. Zeros at 0, 0. Y-intercept at 0, 0. And what else do we need to talk about? Intervals of increase from 0 to infinity. So it always increases. No intervals of decrease. And is this function an odd function and even function? So an odd function, we have a formula. Odd function is equal to f, so f of x is equal to negative f of negative x. So in our case, let's say f of 1 is just 1. And then negative f of negative 1, so f of negative 1 is negative 1. And then negative 1, that's just 1. So this isn't, because this satisfies the odd function formula, this is an odd function. No asymptotes. And because we don't have any asymptotes, this means our graph is continuous and have no discontinuities. Complete the following statements. So, end behaviors. As x approaches a very large value, y approaches a very large value. Very large positive value. And as x approaches a very large negative value, y also approaches a very large negative value. Alright, so that's really fast. Let's go ahead and do the same thing for the rest. So we have a lot of space to use here. F of x is equal to x squared. Domain. X is all real numbers. Range. Obviously we notice a lower point on this graph, so y is all real numbers, but y is greater or equal to 0. So we notice that y always stays above the x-axis. It never falls below it. So we have our first restriction, first change. Zeros at 0, 0, at 0, 0. Notice that we don't have any other zeros. Y-intercept also at 0, 0. At 0, 0. Intervals of increase. We finally have an oh sorry, this one I just made a mistake. Intervals of increase is negative infinity all the way to positive infinity. So the intervals of increase for this one here, 0 to infinity, and intervals of decrease is negative infinity to 0. Is this an odd function or an even function? Now we have to introduce the even function formula. So f of x is equal to f of negative x. So let's say f of 2 is equal to f of negative 2. So let's check in our case. So let's just use f of 2. So using the quadratic in the quadratic function, when we have f of 2, we'll get 4. And f of negative 2 is also 4. That means that we satisfy the even function equation, so this is an even function. And because it's fully continuous, so no asymptotes. And our graph is continuous everywhere and have no discontinuities. As x approaches a very large positive value, y approaches a very large positive value. And as x approaches a very large negative value, y also approaches a very large positive value. As we notice, we never get on in we will never be negative for the y values. All right, 6 more to go. Go ahead and move this a little bit and copy paste text box. Now let's do f of x is equal to 1 over x. Oh, copied it twice. Okay, here we go. So what's the domain? We finally have a change of domain. X is all real numbers, but notice when x is equals to 0, it's not defined. Our function is not defined. We're dividing by 0. We don't know what's division by 0. So x cannot be equal to 0. X cannot be equal to 0. What's our range? Well, range, there is no restriction. But wait, if we think about it, what will get us 0? Notice that if we to check what gets our y value 0, we have to set f of x equals 0. So 0 is equal to 1 over x. But we all know that dividing by 0 is undefined. So to get a 0 y value, the top has to be equal to 0. But because 1 could never equal to 0, that means that y also cannot be 0. Y does not equal to 0. Let's go ahead and check zeros. Notice, because y never equals to 0, we will have no x-intercept. And our y-intercept, because x is never 0, that means there is also no y-intercept. Now let's talk about the intervals of increase. Intervals of increase is where our function goes up. So it goes up and right. So notice that both this goes from left and goes down, and on the right it starts from the very positive value and all the way go down, less positive and less positive. So there is no increase. None. Intervals of decrease. From negative infinity to pot infinity. So notice that because they only have one mode, it's either increasing or decreasing across the entire interval, this is a monotonic function. Only increase or only decrease. Alright. And because we have two asymptotes, x cannot equal to 0 and y cannot equal to 0, these are our asymptotes. Oh, I skipped the even or odd. So notice that 1 over, let's say 1 over 1 is equal to 1. And then 1 over negative 1 is negative 1. But because we had the odd function formula of f of x is equal to negative f of negative x, that means it's an odd function. Function and horizontal asymptote at y equals 0, because x can never be 0. Vertical asymptote x equals to 0, because we won't have any x values here. Our graph is continuous everywhere except when x equals to 0. So that's our only point of discontinuity, where we have an infinite discontinuity. So whenever we have an asymptote, it's called an infinite discontinuity. Let's talk about the x values approaching large values. So as x approaches a very large positive value, notice that 1 over a super large value, eventually it's going to be 0. So y approaches 0. And as x approaches a very large negative value, 1 over something negative, super large negative number, it's still going to be negative, but it's going to be close to 0 again. So y approaches 0. Here we could specify minus 0 and plus 0. And plus 0 means we approach 0 from above. And negative 0 means we approach 0 from below. And you look at this graph on the left and you see, oh, it kind of makes sense. Okay. Alright, let's go ahead and fast forward to our absolute value function that we have explored just last class. So let's go ahead and do this. Where do I put it? Let's put it here. Alright, f of x is equal to the absolute value of x. Domain, x is all real numbers. Range, y is all real numbers, but y is greater or equal to 0. We explored all of this last class. 0 at 0, 0. Y-intercept also at 0, 0. Intervals of decrease. Well, I should do increase first. From 0 to infinity. Intervals of decrease is negative infinity to 0. And notice that it is an even function because it satisfies f of x is equal to f of negative x. Because this holds true, it's an even function. No asymptotes. And because we have no asymptotes, no nothing, our graph is continuous everywhere and have no discontinuities. Let's talk about the end behavior. As x approaches a very large positive value, y approaches a very large positive value. And as x approaches a very large negative value, similar to a quadratic function, y approaches a very large positive value. And quick and smooth, we are done with our absolute value function. Let's go ahead and do square root function. So f of x is equal to square root of x. So this is going to be my notation. I hope you guys could be able to deal with that. Let me paste a new text box. Square root of x. Ugly. Anyways, here we go. So what's the domain? It will be cool if we have the graph here, so I'll type over here on the right, but we still can see a little bit of the graph. So domain, notice that we only have half of this, meaning that we have a fraction of a domain now. So x is all real numbers. But look, x is only defined when x is greater than 0. So x is greater or equal to 0. And if you think about it intuitively, you're like, that makes sense, because we can't have a negative square root, because we don't know how to compute that. Or you do with the imaginary, but it's not on the actual plane, so it's only on the imaginary plane. Let's talk about the range. So range, notice that the lowest value that y can take is also 0. But besides that, y can take every value that's above. So y is all real numbers. Y is greater or equal to 0. So it's the same thing it's the same thing as the domain. Now, 0 obviously at 0, 0. That's our only point. And besides that, we no longer have any x-intercepts, and y-intercept is also 0, 0. And besides that, we also don't have any more y-intercept, intervals of increase. And this is from 0 to infinity. And because this covers our entire domain, so no intervals of decrease. Also hinting that this is monotonic. It only increases. Okay, now let's talk about the end behaviors. Oh, sorry, no asymptotes. And it is not a even nor odd function because you only get half. So because if on any type of even or odd or symmetry, it always have to be across the y-axis or across the origin. Because we only have half of the graph, we can't have any sort of symmetry. Let's talk about the end behaviors. So okay, our graph is continuous everywhere it's defined and have no discontinuities. Alright, as x approaches a very large positive value, y approaches also likely a very positive value, a very large positive value. As x approaches a very large negative value, this case is impossible. So we can't actually approach a very large negative value because it's a square root. We can't take any negative values. Alright, let's go ahead and copy this and do our second last function, which is an exponential function. So unfortunately, we can no longer see the graph. Kind of sad, but that's okay. We'll make a paste and we will take that and put it here. Why don't we make that smaller? So at least we can see the graph. Anyways, let's go ahead and do this. So what is the domain? We notice that we could put anything into this function and we will still get a resulting y value. So x is all real numbers. Range. What is a range? Notice that we could never make this thing 0. No matter how small this exponent is, it's always going to be 1 over something. It's never 0. So, and also, notice we can't make it negative. We can never make y negative. No matter what power we raise it to, it will never be negative. So range will be y is all real numbers. Y is greater or equal to, only y is greater than 0. So in this case, it's no longer greater or equal to, it's only greater. And let's talk about zeros. Because it never intersects the x-axis at any point. None. Y-intercept though, we do have an y-intercept. So what 2 to the what power is 1? Right? It's 0. Or if you want to do it the other way around, 2 to the 0 power, anything to the 0 power is always going to be 1. It's just 1. Right? So 0, 1. And let's talk about intervals of increase. Notice we have another monotonic function. So across the interval of negative infinity all the way to infinity, it's always increasing. It never decreases. Never. Intervals of decrease. None. Alright. And because this is an asymmetric function, we could obviously tell by the shape it is asymmetric. So neither even nor odd. And we also have, here's the point. I almost got ahead of myself. Here's the point. Because as x goes really small, really negative, let's say negative 100 billion. To translate that, the negative sign will become 1 over. So 1 over 2 to the 100 billion. That is very close. That is very much close to 0. In fact, you could even say that is exactly 0 if you want to estimate it. So we'll see that it approaches, as x approaches very negative number, y will approach 0, but it will never reach 0. So that introduces our horizontal asymptote at y equals 0. However, because it's a horizontal asymptote, our graph is still continuous here as everywhere and have no discontinuities. And now let's talk about the end behaviors, which we already talked about. One of them is as x approaches a very large negative value, y approaches from above. Now we gotta talk about the other case, which is as x approaches a very positive, as x, oh, my spacebar isn't working. Don't know what happened there. As x approaches a very large positive value, y approaches infinity. Or to say, a very large positive value. Here we go. Now we are finally at our very last function, the sinusoidal function. I'll just cover that up. We're gonna delete it later anyways. So let's look at this. We will have f of x is equal to sine x. So we could obviously use cosine x as well because we learned that last year, but we're not using it in this case. So we're just gonna use sine x. It doesn't really matter. So let's talk about the domain. So what can we put in here? So we can put x as any real number, right? Because no matter what we put into sine x, it's always gonna give us a number. But range, here's an interesting part. It is bounded. Notice when we look at this graph, sine x is a bounded function. Negative y is all real numbers, but -1 is less or equal to y is less or equal to 1. It's bounded from -1 to 1. Y could be any value in between, but it could never exceed this. It can't go anywhere else. Alright, let's talk about the zeros. There is an infinite amount of zeros. And it's at 0, 0, at 0, 0. Now let's think, what makes sine of x 0? So notice we already see here 180 degrees and 360 degrees makes it 0. So 180, so 0, 0. And at any x equal to 0 plus 180 n, where n is equal to, is all whole numbers. Whole numbers. It could be -1, -2, 3, 4, whatever. As long as x equals to a multiple of 180, it will be negative. As long as it's equal to a multiple of 180, we will have a 0. And y-intercept. This is much easier because there's only one y-axis, so y-intercept is 0, 0. Let's talk about the interval of increase. Just know there's a lot because it's always fluctuating. It's going up and down here and there. So we won't specify, and we will leave it for the trig function unit. And we could say the same thing for intervals of decrease. A lot. All right, let's talk about. Okay, so no asymptotes. So is sine function an even function or an odd function? So how do we know if it's an odd function right away from the graph? Well, if you rotate it across the origin, you rotate it 180 degrees around, and it's the same thing, it's an odd function. So sine function is actually an odd function. And our graph is continuous everywhere and have no discontinuities. As x approaches a very large positive value, y fluctuates. As x approaches a very large negative value, y fluctuates. So no matter what we do in this case, y will always fluctuate, and we are not certain about what happens when x becomes very large or x becomes very small. Now let's go ahead and move on, as we have now introduced ourselves or reminded ourselves to all of these parent functions that we have learned last year. Now let's connect the graph of a function with its characteristics. So let's see. Let's talk about the characteristic first. So range will have y is greater than 0. So which one of these matches that? Well, we see both of these matches it. So we cannot make anything about this. So let's move on to this. X is all real numbers. We look at all of these graphs and realize, hey, wait a minute. Every one of these graphs have this exact domain. This is the exact domain. Every graph could have this domain. Alright, I guess we can't do anything as well. So now let's look at the infinite number of zeros. Whoa, that's helpful. That means that this can't have infinite number of zeros. That's 1 0. This have no x-intercept. This only have one x-intercept. The only function to have an infinite number of zeros is the sinusoidal function. Sine of x matches this. So it's easier for us to make decisions about other now that we're doing elimination. So let's go ahead and talk about as x approaches negative infinity, y approaches 0. So which of these functions does that? So we know that that absolute value function will never be negative. And especially when we got very positive, we'll also approaches a very large number. We won't approach 0, no matter what. And for x, we could picture for f of x equals to x, a linear function, we could picture the same thing. A very large negative number is also going to have a very large negative number on the y side. So the only function that matches this description is 2 to the power of x. So we matched 2. Now we're left with these and the first two. So obviously we can tell the range one belongs to absolute value. So we could get rid of that. And now domain is all real numbers. It's obviously the linear function. And we are done. Let's go ahead and get to example 2. Let's go ahead and we're given some characteristics of a random function, and we may be able to determine the equation of the function. Maybe. Using reasoning to determine the equation of a parent function. So let's look at this. Right away we see domain. That doesn't really help. But we see range. Hey look, it's bounded. What does that mean? It's a sinusoidal function. It could be y equals cos x, y equals sine x, whichever you want. Right? Because we know that no other parent function in this entire list, no other function, have a bounded range. So we know the only function here is sine of x. Connecting the characteristics of the function to its equation. Which of the following characteristics of the parent function p of x is equal to 2 to the power of x? Justify your reasoning. The function is decreasing for all values. That is not true. Remember, we said this is an exponential function. This doesn't make sense. Every x value after is always going to be larger, so it's always increasing no matter what. It's always increasing, so A is automatically false. The graph is continuous for all values. That is true. There is no discontinuities. The function p of x is an even function. That is not true, because 2 to the power of x is not symmetric in any shape or form. And the function has no zeros. That is true. So it's false, true, false, true. And last, let's go ahead and do example 4. Connecting the characteristics of a function with its equation and its graph. Determine a possible transformed parent function that has the following characteristics and sketch the function. So right away we see the domain. Okay, x equals to all real numbers. Yeah, does that help? Not really. Every function pretty much has a domain similar to this. So let's go ahead and try something else. Look at the range. So y is greater or equal to -2. Does that help? Certainly. But what helps even more is the decreasing and increasing interval. When you see negative infinity and 0 seems to be that turning point where on the left of it increases, on the right of it it decreases, and on the right of it increases. So which function does this remind you of? That you have worked a lot in grade 10. It's a quadratic function, right? Think about it. It's the quadratic function. When you have a quadratic function, the left is going to be decreasing and the right is going to be increasing. That's how simple it is. Let's go ahead and give that a little sketch. And notice that when we have the range of y is greater or equal to -2, that also matches. So this is our function. And we are done. Alright everyone, I hope you took something away from this class. There is homework for you on the textbook attached in the comment section if you're watching from YouTube, and if you're in my classroom, it is given to you. And there's questions on page 23, 24, 25. And right after today, we are going to do a short test that I'm planning, and I'll go through a mid-chapter review with you guys, and we'll get ready for our first assessment.